This is part 2 of the free vibration video, free vibration with damping. Recall that this is the system that we are looking at, mass, spring, damper. And this is the equation of motion, mx double dot plus cx dot plus kx equals 0. The natural frequency, the natural angular frequency is omega n square root of k over m. We define this thing called the damping factor, the damping ratio, zeta, which is c over 2m omega n. Then we rewrote this equation in terms of omega n and zeta and got this equation, which is x double dot plus 2 zeta omega n, x dot plus omega n square x equal to 0. And this is a second order differential equation, which for which we said let's look for solutions of this nature. We got this characteristic equation, which is a quadratic equation which we can solve. And the two solutions that we get are lambda 1 and lambda 2. Which are given by this quantity, omega n minus zeta plus minus square root of zeta square minus 1. Okay. Now, we can say lambda 1 is the plus version and lambda 2 is the minus version, right? So let's say lambda 1 is omega n minus zeta plus square root of zeta square minus 1. And lambda 2 is omega n minus zeta square root of zeta square plus minus 1. Okay, so those are two equations. Let's call that equation 11, those two things, equation 11. Okay, here are a few different cases. There are three cases which correspond to whether lambda 1 and lambda 2 are real valued, complex valued, or involve having equal roots. Okay. Okay, case 1. So just think about when this quantity would be complex valued. It'll be complex valued if the thing that's inside the square root is negative, right? So let's call that case 1. Well, case 1, let's actually consider the case when lambda 1 and lambda 2 are both real. Which corresponds to, so let me just pull this down a little bit. So case 1 corresponds to zeta square minus 1 greater than 0. Okay, or zeta is greater than 1. Okay, this case is called over damped. Okay, so when zeta is greater than 1, zeta square is going to be greater than 1, and the thing inside the square root is greater than 0. Therefore, this is real valued, this is real valued. Okay, zeta square minus 1 is greater than 0, I mean. Okay, so both real valued roots implies solution is just, it's still the same as what we had before, no change necessary. If lambda 1 and lambda 2 are just real valued, we can just leave it as it is. It's equal to a1 e power lambda 1t plus a2 e power lambda 2t. Okay, so that is a solution. If zeta is greater than 1, you will notice that both these quantities will be negative. Okay. You can think about it. Well, first of all, omega in some positive number, this root is clearly negative because it's the sum of two negative numbers. This root, it's negative zeta plus square root of some quantity. This quantity is zeta square minus 1. If you take the square root of just zeta square, this will be zeta square, square root of zeta square, and these two will exactly cancel. This is a quantity that is less than zeta square. So if you take the square root, you get a quantity that is less than zeta, but a positive number, and then you subtract zeta from it, you'll get a negative number. Okay, so if zeta is greater than 1, both these quantities are going to be negative. Okay, so this is going to be the solution where you find A1 and A2 using initial conditions, of course, as usual, whatever they may be. And the fact that lambda 1 and lambda 2 are negative, in other words, these exponents are negative, means that if you want to plot the x of t as a function of time, it might look like this. So it might look like this, or it might look like this. So essentially, pure exponential decay. Okay, solutions will look like this or that. There is no oscillations. Surprisingly enough, there is no oscillations. So this case corresponds to you pull it and let go, and the system just comes back to zero because the spring is pulling it back, but it comes back to zero in a manner that there is exponential decay. It slowly comes back to zero. Here, we've given it some initial velocity, so it goes further from zero, but then the spring pulls it back and the damper slows it down, and then it both the speed and the position decays exponentially to zero, right? So this is the situation that's called overdamped, where there's no oscillations, very important, no oscillations. And the system, when pulled away from the equilibrium position, just exponentially decays back to the equilibrium position, namely x equals 0. This is in fact the situation that you would find in a door closer, for instance, or very close to overdamped perhaps, where you have very high damping. That's why it's called overdamped. And the damping is so high that there is the oscillations that would arise in the absence of damping are completely prevented. Okay, so that's overdamped, which corresponds to two real roots, and both real roots are negative, which basically means exponential decay. Okay, because e power negative something t goes to 0 as t goes to infinity, right? So okay, so that's called overdamped. Case 2 is what's called underdamped, and you can guess what the situation may be there, which corresponds to zeta less than 1 or zeta square minus 1 less than 0. So your lambda 1 and lambda 2, these two quantities, the quantity inside the square root is going to be negative. So if you take the square root, it's going to be plus or minus I some number. Omega n minus zeta plus minus, well, of course, it's this thing, but this thing is negative, so you can write this as minus zeta plus minus I And then this thing inside the square root is a positive number, so it's you're sort of taking -1 out, which becomes I, right? And what we are going to we're going to slightly rearrange this to I omega n square root of 1 minus zeta square. Um, and we're going to call this thing omega d, okay? It's going to be equal to minus zeta omega n plus minus I omega d. Okay, so those are the lambda 1 comma lambda 2, where omega d is omega n square root of 1 minus zeta square. Okay. Okay, so what does this all mean? We have two complex valued lambdas. If we leave the solution in this form, lambdas are complex valued, which means that a1 and a2 will be complex valued, which is sort of an inconvenient form for the solution. Instead, it's better to write the solution in the following form. The solution for x of t can be rewritten as follows. Using this thing called Euler's formula. Lots of things in mechanics are unfortunately named Euler's. Euler's formula, which basically says e power theta equals cosine theta plus I sine theta. Okay, so this is called Euler's formula. So essentially this e power, this thing, we are going to replace with a cosine and a sine. So it turns out that we can write it as x of t equals some a1, not necessarily the same a1 as before, a1 times e power minus zeta omega n t, and then within brackets, actually you can put the a1 inside, a1 cosine omega dt plus a2 sine omega dt. Okay, so this is the general solution for underdamped situation. Namely zeta less than 1. What does this solution look like? We saw what overdamped solutions look like. They just sort of decay exponentially to 0. Underdamped solutions look like this. So if you take a look at, well, let me actually unpack this expression. Let me just write it again so that it's convenient here. Okay, cosine omega t plus a2 omega dt, I suppose. A2 sine omega dt. This expression is just a pure exponential decay, right? That's just exponential decay as a function of time. This expression is going to be basically some oscillation, a persistent oscillation, right? Because it's just some constant time cosine plus some constant time sine. So that's a persistent oscillation. So when you take the product of an exponential decay and the persistent oscillation, you actually get something that looks like this. So this is going to be x of t. X of t might look like an oscillation that slowly dies down. And the peak of these oscillations are separated by 2 pi divided by omega d instead of omega n. Okay, so this is the time period. And the time period of oscillations as it decays is actually 2 pi by omega d instead of omega n. In other words, the frequency with which the thing oscillates gets modified because of damping a little bit. Okay, so that's underdamped. Okay, overdamped, no oscillations. Underdamped, decaying oscillations. Okay. Decaying oscillations, underdamped. So that was zeta less than 1. And then there's this sort of boundary between overdamped and underdamped. Case 3, which is called critically damped. Which is zeta equal to 1 or zeta square minus 1 equal to 0. So what we get is lambda 1 comma lambda 2 is omega n times minus zeta plus minus square root of zeta square minus 1, which becomes 0. So all we have is, so this is what you would call repeated roots or equal roots for the quadratic equation, 2 equal roots for the quadratic equation. And in this case, it turns out that x of t, I'm not going to derive it, x of t equals, so general solution in this case looks like a1 plus a2 t e power minus omega n t, okay? So these are 3 main cases. This also looks like no oscillations. So if we start it with x of some x of t, it will sort of decay to 0, but not as fast as it would in the overdamped case, okay? So this quantity, of course, increases linearly with time, but because this quantity decreases exponentially with time, this wins out so that there is still effectively an exponential decay of the solution. Slightly slower than exponential decay, ever so slightly. Okay, so it's interesting to understand the significance of critical damping. It turns out that a lot of systems are designed to be critically damped. So like we said, underdamped systems have oscillations. Overdamped systems have no oscillations. If you want a system to come to x equals 0 as fast as possible, but without oscillations, it turns out you want to be at critically damped, okay? So damping slows things down. And sort of reduces oscillations. Critical damping is the fastest to x equals 0 without oscillations. Okay. In other words, if you have more damping, it will approach x equals 0 much more slowly. If you have less damping, there will be oscillations. And critical damping is the fastest to approach x equals 0 without oscillations. So you will learn about this if you do a feedback control class. Again, a lot of systems are tuned to be near critically damped. Okay, So of course, so those are the three big cases. Really what we want to take away are these formulas. This is the formula for underdamped. This is the formula for overdamped. And this is the formula for critically damped. And we will put these formulas on the formula sheet, I guess. Of course, there's case 4, which is no damping, which we've already seen, which is just a special case of this guy, right? So for no damping, this term becomes equals 1. It's a special case of case number 2, underdamped, and then all you're left with is this case, okay? This is a special case of case 2 with zeta equals 0, omega d equals omega n. So what we have is x of t equals a1 cosine omega nt plus a2 sine omega nt. And that's it, because e power minus zeta omega nt is equal to e power 0, which is 1. Okay, that's case 4, which is something that we discussed completely separately in the previous lectures. Okay, so those are all the expressions for the solutions for x of t given given a system with a mass, a spring, and a damper.